Good morning. So today what we're going to do is a continuation of Unit 3. This particular presentation for Math of Business Applications, Business Statistics, is going to be not from your textbook, but instead this particular presentation is from your course supplement, which is available on Blackboard in your course documents, syllabus, and schedule. It's from part 9 specifically. So we have some goals for this particular presentation. We want, first of all, for you to be able to explain what dispersion is. What do we mean by using that word? As a part of dispersion, we're going to talk about the range of a data set and the standard deviation. We want you to be able to use the standard deviation in a comparison of two different sets of data. And we want you to be able to identify the formula for what is known as a sample standard deviation. That's important because a lot of what we're going to be doing is just sample. And if you go out on a Google search, and I know some of you will, you're going to find a standard deviation formula that is not what we're using in class. So you want to make sure to be Googling sample standard deviation. And we're going to show you that formula and translate the different parts of it so that they're recognizable to you and can be used. And we're going to have you use that formula to calculate the standard deviation by hand for a small data set, not for a large data set. That's too much. I once spent an entire weekend doing that by hand. Ugh. All right, so first thing, what is dispersion? Dispersion, the word itself, is like to disperse. When you see a crowd disperse, it's about the crowd spreading out and not being concentrated. So oftentimes when we look at two different sets of data, we will find that a lot of their information is very close. They may have the same range, they may have the same mean, but one characteristic that we can look at is how spread out the data is. That is, how far each data point is from the mean of that group and how far each data point is from each other. To do that, we use two different ideas of dispersion. In both of these ideas, the smaller that number is, the more consistent or close together our data is. So the first one is just, it's the quick and dirty. The first one is the range. The range we talked about when we did measures of center. The range is the difference between the largest value in your data set and the smallest value in the data set. It's really easy to find. You simply order that data. Of course, if it's really small, you may be able to just visually see it. You want to find the lowest point and the highest point and determine the difference between those two. So you just want to subtract them. That is your range. So if you're given 10 points, like I have been here, and these are in order if you read them horizontally, row by row, rather than by column, you will see that the lowest number is 12 and the highest number is 62. To calculate the range, we simply find the difference between 62 and 12, and we get 50. This is really easy to compute, but, however, it is not often reliable as a measure of dispersion. It doesn't really give us much of a story. It's based on only two values in the set. So, while the range of 50 tells us very little about how spread out the data is. Look, for example, at this same data set in blue. It's not the same as the original one. It's slightly different. But if you look at the lowest number, that is indeed 12, and the highest number is 62. So the range of this data set is 50. But if you look a little closer, you will see that we have 9 12s and a 62. So if this was, let's say, the price of dinner, how often I eat out, and most of the time I eat a $12 dinner, and then one day I did a $62 dinner. Saying that the range of prices of food when I eat out is $50 is true, but in terms of my actual habits, you see that most of the time I eat a $12 meal. Maybe once every 2 weeks, I might throw in an expensive meal. Right? I have a range of 50 with a very similar data set in which I have just one $12 meal and all the rest are $62 meals. This tells you that I'm maybe a little posh, hoity-toity. What are some of the that I have money to spend on dinner, and very infrequently do I eat something that is a cheaper meal or maybe fast food. Most of the time I'm eating a $62 meal, and here, as well in many other places, that would be a very nice sit-down dinner with probably quite a few drinks. All right, notice both of these have a range of 50, but they represent very different sets of data from which we could draw very different conclusions. So while range does tell us how spread out the data is, it doesn't tell us much about the data itself. All right. For that, we often use what's known as a standard deviation. The standard deviation is a measure of how spread out the data is from the mean or from the average. So it lets us know if the data has a lower standard deviation or a higher standard deviation. When you have a lower standard deviation, what happens is the data itself is clustered together. It happens to be very closely clustered. A higher standard deviation means that your data is going to be more spread out. It's sort of across the board. I often put up these two targets and say, okay, so if you are on a dart team or an archery team or a gun range, right? Who do you want on your team for target shooting? There's no consistency with the second option, the one on the right. They're sort of all over the place. You don't know if they're going to be able to hit a bullseye. You don't know how many points they're going to be able to score. And while that may also be true with the one on the left, there is some consistency. You know that they've got a sort of, I guess it would be a right-hand pull to all of their shots. Now, which one, if you're teaching, do you want to teach? Well, I don't know. That one's kind of up for grabs. Some people would choose the one on the right simply because they really haven't developed any bad habits other than just being bad. And the one on the left here, this guy, well, they're pulling to the right, so they may have some habits that are going to be difficult to break. I don't know. All right, so what does it look like in terms of our histograms? Well, when we're looking at our histograms, a lower standard deviation will have everything really close to the mean. Do you see how it's really tall and everything is concentrated near the middle? That is a lower standard deviation. A higher standard deviation, our histogram is going to be really spread out and it's going to be sort of flattened. The consistency happens with the tall, skinny, and then less consistency with the short and fat. That means that it's more reliable data in the consistent one. And by reliable, what we mean is it's easier to sort of give a consistent range, give a good guess as to where things are going to be, where the data point is going to fall, versus the higher standard deviation where we really don't know necessarily, since it's spread out over more of a range, we really don't know where that data is going to fall. We then take those histograms, we take those histograms and we convert them into the normal curve. The normal curve is a curve that we use where we sort of connected all the histograms together to give a smooth line view of a histogram. So again, the lower standard deviation is sort of tall and spiky in the middle. It's closely clustered around the mean. The higher standard deviation is more spread out. The points can be further from the mean. The lower standard deviation is considered to be consistent versus less consistency and more variability in the higher standard deviation. More reliability for your data in the lower standard deviation and less reliability in the higher standard deviation. Now, what we're going to be doing in this course is known as a sample standard deviation. The sample part simply means that we are assuming that we are not using all of the data points when we make our calculations. That all of the data points would be too much. So we're using a sample. For example, I think I've said before, if we were taking the height of all of the point guards that have ever played basketball, in order to do a standard deviation of that, a population standard deviation would take every point guard ever. We're not doing that. We would be taking a sample standard deviation. And that sample standard deviation has 4 main parts to the formula. The first is that we're using a sigma, or a total. That little Greek letter, just like we used it in mean, means that we're going to total up or add up. What we're adding is the x minus x bar squared. This is the difference between the data point and the mean squared. We're going to divide that by 1 less than the number of data points in our set, in our sample set, and then we're going to take the square root of that number. This gives us a really ornery looking formula where s is equal to the square root of the sum of x minus x bar squared all over n minus 1. This is our formula for the sample standard deviation. Again, each part, the Greek letter, the one that looks like an E, means to sum up. The x is just a data point. The x bar is our mean, so we're going to take x minus x bar and square that. That's all the things that we're summing. We're going to take that total and divide it by 1 less than the number of data points. Once we have that number, we're going to take a square root. Okay, this is a lot. So we're going to run through the steps one more time. In order to calculate a standard deviation, we recommend that you order your data. Again, for really small data sets, you might not have to do this. We want you to find the mean of that data. That's our x bar. Now, we're going to determine the difference between each one of our data points and that mean, and then we're going to square that distance or difference. This will always be a positive number. If you're typing it into your calculator and getting a negative number, that is because you are typing it into your calculator incorrectly. Remember, a negative times a negative is a positive. So even if the difference is a negative number, when you square it, you should get a positive number. All right, this is where our sigma comes in, that Greek E looking letter. Now we're going to add up all of these squares. Every number that you squared is going to get added up. Once we have that sum, we're going to divide by 1 less than the number of data points, and then we're going to take the square root. Again, that is your standard deviation. All right, now, here I have standard deviation for the same 10 data points that I used earlier in this particular presentation. So, we want to do, data points are in order. Yes, they are. So the second step is to find the mean for the data. In order to find the mean for the data, I need to add up the 12, the 23, the 27, 29, 36, 44, 45, 52, 60, and 62. If I add all of those up, I get a total of 390, which I then need to divide by the number of points in this data set, which is 10. Okay, done. 390 divided by 10, which is 39. I now know that the mean or average for this data set is 39. I'm going to use that mean, and I'm going to subtract every data point from it, or every data point minus the mean. Then I need to square that. So I like to use a table. I'm going to populate a table here in just a second. That first column, notice, is the data point. The second column is the mean. The third column I'm using is data minus mean, and then the fourth column is the square. I like to use this table just because it helps me organize as I go. I'm not saying y'all have to, but with 10 points, it's kind of helpful to have a way to organize. And it has a way, it's a nice way for me to explain. So there's that too. Okay. So find the difference between each data point and the mean. My first data point is 12. I'm going to subtract from that the mean. So 12 minus 39 is a negative 27. I now need to square a negative 27. I need to know what this number is squared. So negative 27 squared is 729, sorry. Notice a negative times a negative is a positive. So we do want, hello, yeah, negative times a negative is a positive. Good. All right, next point is 23 minus 39. That's a negative 16. When I square that, that's 256. 27 minus 39 is a negative 12. Negative 12 squared is 144. 29 minus 39 is a negative 10. 10 squared is 100. 36 minus 39 is negative 3. Squared is 9. 44 minus 39 is 5. Squared is 25. 45 minus 39 is 6. Squared is 36. Then we've got 52 minus 39, that's 13, squared is 169. 60 minus 39 is 21, squared is 441. 62 minus 39 is 23, 23 squared is 529. Notice all of this last column is positive because whether it's a negative and you square it or a positive and you square it, that should always end up to be a positive number. So, quick aside, if I were to add up all of these, the negative 27, the negative 16, the negative 12, the negative 10, the negative 3, 5, 6, 13, 21, and 23, I should get 0. That's because we're determining every data point's difference to the mean, and if the mean is in the middle, I will have just as much value above as I do below. So the difference between the total above the mean and the total below the mean should always zero out, right? It's a mean, it's the middle. So I'll have just as much above as I have below. So if I add up that data minus mean column, I'm going to get 0. So if you're adding stuff up and you get that 0, you're adding up the wrong column. You need to add up the squared column. The x minus x bar squared. Add up that column, all right? So here we go. If I add up the 729, the 256, the 144, the 100, the 9, 25, 36, 169, 441, and 529, I am doing what's called the sum of the squares. And if I sum up those squares, I get 2,438. That is the total sum of the squares, which I have to divide by 1 less than the number of data points. There were 10 data points, so I'm going to divide this by 10 minus 1. That's 9. I need to take the square root of that answer. So I'm going to do 2,438 divided by 9, and I'm going to put that all underneath a square root. Then I'm going to take the square root of that number. I should get approximately 16.5. This is our standard deviation for this data. 16.5 tells me 2 things. It's a pretty high number, so it tells me that this data is fairly spread out from the mean and from each other's. The other thing that this gives me is a class width. This gives me the width of the histograms. We don't use it very often because 16.5 is not a good one to use in a basic class. So what I need you to understand is that it's how spread out the data is, and it can be used as the width of your histogram bar. So if you started at 0, you could go to 16.5, and then you could go to 16.4, and then it would be 16.5 to 32.9. You can keep adding 16.5 on, okay? All right, so next, what I want you to do is to try it for yourself. And this particular problem actually comes from real life. One of my really good friends of, over 20 years, Christine. Christine and I used to waitress together at the Olive Garden when it very first opened here in La Crosse. And she has since gotten a job working, she managed Barnes & Noble here in La Crosse for a bit. just a quick minute, assistant manager, and then moved on to manage Barnes & Nobles in Rochester and Milwaukee. And she has since transitioned into a different position working for a not-for-profit. But Christine is one of my favorite people in the whole wide world, and she is math challenged, to say the least. So she actually did call me one day, and she was very upset because in her position as manager, she was doing the schedule, and she had 3 employees who had come to her and said that they were very upset with the unequal distribution of the hours. So Christine pulled up their schedules for the last 6 weeks. This is on my recommendation. I said, okay, let's get their schedules for the last 6-ish weeks. And I have messed with the numbers here some, just sort of to keep all anonymity. But we did pull up the schedules for the last sort of 6 weeks, and we looked at the average hours that each person had worked, and they were fairly the same. Well, they weren't exact, but they were pretty close. And we looked at the high number of hours and the low number of hours, and that the range was pretty close. And so I said, okay, let's see if we can do some standard deviation, and let's see if we get any obvious sort of glaring issues. So that's what we did. Now, I've put this together in a problem for you. We've got 3 people, Karen, Martin, and Rory. They're Doctor Who names. Karen, Martin, and Rory. And we're going to take a look at the range, mean, and standard deviation for each one of them over the last 6 weeks. And what we want to determine is whether or not anyone's schedule is particularly inconsistent. Does anyone have a claim against Christine, or can we validate their claims that their schedule just varies too much and that there's no consistency in it and that it's unfair to them? So here's what we're going to do. All right. On this slide, I have put together just the little table because I find it so much easier to do. And so we're going to take a look for Karen in orange, for Martin in red, and for Rory in purple. And we're just going to go through this process of finding a standard deviation for each one of them. Now, I'm going to do Karen and Martin. Rory's a little hit and miss because my lovely face is going to be sitting on top of Rory's table. But when you look at the PowerPoint for this information, which is also available on Blackboard, you will be able to get through it. You'll be able to see it all without me covering it up. All right, so for Karen, we've got this last 6 weeks. The lowest number was 20 hours. Then she had 27, 29, 31, 33, and 40. So we're going to find the standard deviation for this. In order to do that, well, first let's take a look at the range. And if we take a look at the range of hours is from 20 to 40. So she's had a 20-hour window. In order to do the standard deviation, we need to know the average number of hours. So we're going to add up 20, 27, 29, 31, 33, and 40. This is the sum of all data divided by the number of data points. So this would be 180 divided by 5, which is 30. So on average, she works 30 hours a week. Now, to find the standard deviation, we're going to use the formula, which is the square root of x minus x bar squared summed up divided by 1 less than the number of data points. So in order to find all the pieces of this, this is where I'm going to go to the table. First of all, I'm going to put those 6 data points in under my x, and then my x bar is the average. This was 30. Now, I can write 30 down multiple times, or I'm just going to draw an arrow and say, okay, all of these are 30. So then I'm going to do x minus the x bar, or 20 minus 30. That's a negative 10, which when I square it, I get 100. Then I have 27 minus 30, which is a negative 3. And when I square a negative 3, I get a positive 9. 29 minus 30 is a negative 1. Squared is 1. Then I'm going to do 31 minus 30. That's 1. And when I square that, that's still 1. Then 33 minus 30 is 3. And when I square that, I get 9. And then 40 minus 30 is 10. Squared is 100. So I've now squared all of the differences, so I need to add up those squares. That's the 100 plus the 9 plus the 1 plus the 1 plus the 9 plus the 100. And I need to divide it by 1 less than the number of data points. Since I had 6 data points, I'm going to divide this by 5. This gives me 220 divided by 5, which is 44. And I need to take the square root of that 44. Now, 44 is not a perfect square, so it's not going to work out real slick, but I can figure out that it should fall between 6 and 7, because I know 6 squared is 36 and 7 squared is 49, and 44 is between those two perfect squares. So it should be between 6 and 7, and when I type square root of 44 into my calculator, sure enough, I get 6.6. So this data has a standard deviation of 6.6. Our range is 20 and our mean is 20. And so now with Karen done, we're going to take a look at Martin's. So same process. The range for Martin is 20 from 40, which is 20. The mean would be the total of all of the data points, the 20 plus the 29 plus 29 plus 31 plus 31 plus 40. And I want to divide that by the number of data points. That's 6. So I have 180 divided by 6, which is still 5. This is a mean of 30. I'm going to use that mean and my data points and the table in order to figure out my standard deviation. It's just helping me to organize the data. So all of my data points, formula first. All of my data points go in under X. The X bar is my mean, that's 30. And again, I can put in that first one and then just drop an arrow down to tell the world that 30 goes in every one of these in this column. And then I'm going to fill in the third column. So I'm going to do 20 minus 30, which is negative 10. And then I'm going to go straight to the fourth column and do a negative 10 squared, which is 100. Then 29 minus 30 is negative 1, and when I square that, I get 1. And again, I love it when they're duplicates, because once I've done it, I know the data. So negative 1 squared is 1. 31 minus 30 is 1. Squaring a 1, I get 1. Again, for the second one, same data, gotta love it. 40 minus 30 is 10, and when I square that, I get 100. Now, according to the standard deviation formula, I need to sum up this last column, the X minus X bar squared. So that's going to be 100, 1, 2, 3, 4. I'm going to have 204, which I need to divide by 1 less than the number of data points. I'm just noticing something. Guys, these should be 6s. I'll have to fix that. These should be 6s. Hello, Amy. Having a moment. There we go. This is N. These should be 5s. These should be 6s. Okay. So I divided right, but I had the wrong number in there. I'm going to have to fix that before I post. I will fix the PowerPoint. I'm not going to redo this video. Sorry. Okay, so 204 divided by 5 is 40.8, and I'm going to need to take the square root of 40.8. Again, I don't know what that is. It's not going to be a very nice, neat number. That's why we have our calculators. I do, however, know that 40.8 is between the perfect squares of 36 and 49. And the square root of 36 is 6, and the square root of 49 is 7. So this has to be between 6 and 7, and when I take the square root, I get 6.4. Now notice, Martin's and Karen's standard deviations are not that far apart. So whatever result we come to for Karen, it'll be pretty much the same result for Martin, because their standard deviations are super close. But Rory also has a leg in this game, so let's see what Rory's comes out to be. The range for Rory is 20 to 40. That's difference of 20. The mean would be the total of all of those, the sum of all the x's divided by the number of data points, which is 6, and I can't There we go, fixing, come on, fixing to 6, there we go. And 180 divided by 6 is indeed 30. So this gives us a mean again of 30. Now the standard deviation is the sum of all of the x minus x bar squareds, or the sum of all the differences from the means, divided by 1 less than the number of data points. So my head is covering all of this, but if I put this all in and add up all of my x minus x bars, we will get a total of 490, which we will then need to divide by 5. 490 divided by 5 is 98. The square root of 98 is also not going to be a perfect number. But I do know that 100 is awfully close to that, and the square root of 100 is 10. So this standard deviation should be really close to 10. And sure enough, when I put that into the calculator, that's what I get. I get a standard deviation of 9.9. All right, so this slide is kind of full. Hold on. All right, this is what we started with. I'm going to write down the range, the mean, and the standard deviation for Karen, Martin, and Rory. So Karen's range was 20, mean was 30, standard deviation was 6.6 hours. Martin's range was 20, mean was 30, standard deviation was 6.4 hours. Rory's range was 20, the mean was 30, standard deviation was 9.9 hours. This is kind of ugly being over the top of that, and I might need to move that up so that you can see it all. And then I'm going to put the names back up there. Okay. Now, does this help Christine? If she sees that Karen has a range of 20 hours with a mean of 30 and a standard deviation of 6.6 hours, Martin has 20 hours, or range of 20 hours with a mean of on average of 30 hours and a standard deviation of 6.4, and Rory has a range of 20 hours with a mean of 30 hours, standard deviation of 9.9 hours. Is any one of these 3 workers have a less reliable schedule than the others? Not necessarily less reliable overall, but just in comparison to the others. Which one of these particular pieces of data, the range, the mean, or the standard deviation, is pointing that out to you, and how? Okay. All right, so there is in the actual PowerPoint another video tutorial of someone using a very similar process to get the standard deviation. They do talk about something called a variance. Variance is another measure of dispersion. We are not going to go into variance. It is just a step on the way to finding the standard deviation. So he may mention it in this particular tutorial, but you do not need to know what a variance is. As we end this, can you, here's your check, can you explain what dispersion is? Do you understand it enough to give somebody an explanation? Can you explain to someone else what range is for a data set? What about standard deviation? Do you feel confident enough that you could explain to somebody what standard deviation is? Could you use it as a comparison for 2 data sets? Could you tell somebody else what standard deviation tells you about a data set? And can you identify the formula for standard deviation, including all of the parts, and calculate a small sample set of standard deviation by hand? Okay. All right. Here I have another Doctor Who video. This is one of my favorites. This is Tom Baker. He's one of the originals. There is practice of standard deviation in your supplement in Part 9. On page 26, you can do problems 1 through 4. The answer key is available. And there is a graded homework assignment on WebAssign called Standard Deviation. And as always, if you have any questions or concerns, please don't hesitate to contact myself, your math support person, and or the Math Center. We are all here to help you.